Good afternoon again. So this is a CS 6210 course, right? Hope you are in the right class. And okay. So the first few minutes I will spend discussing the course, the objectives, and what the expectations for the course are in terms of assignments, tutorials, and so on. Okay. So this course is in the R&T slot, which many of you probably know and have taken. So the theory part, this is a 4 credit course, right? So the theory part for this course will go from 2 to 3:15 on Wednesdays and Fridays. Then we have another 50 minutes total for tutorials. Tutorials would be normally problems that you work out in class. There is no lab component for this course. What will be the tutorials? Will be primarily problems. As we go into all of the math part later on, there will be some examples and so on you will work out in class. So the course objectives is to understand basically performance evaluation, right? Performance evaluation of systems in general. Performance evaluation applies to any kind of system, right? Any system that you build, you can measure performance and see whether one is better than the other. You can apply to mechanical systems, electrical systems, and so on. This course will try to focus on techniques most relevant to computer systems, right? So systems, we will talk about examples of those systems. So computer systems, and because I am also a computer networking person, there will be more emphasis on examples from computer networks, right? And in terms of the prerequisites for this course, I expect that you have basic background in, I said basics of probability and statistics, which I think most of you have, some of you have had but think that you do not have. We will see as you go along, right, if you think that your background is adequate or not, right. But there will be a fair bit of mathematics involved, but I do not think it is of the order of like a statistics course, right, there where you have to go into that much detail, but there will be still math, especially for the first half to one third to one half. You will have to deal with a lot of the mathematical concepts, okay. So be prepared for that, and that is why all these tutorial problems are primarily for the mathematical part of things. So that is the first part, and this is ideally a course taken in the 7th semester. So I think some of you are in the 7th semester for the BTech students, right, or dual degree students. So I prefer that you have had an OS course completed as well as networks course completed, right, because some of the examples will make sense only when I talk about. It does not need you to remember all the details of your operating systems course or computer architecture course, but sometimes if you say I am going to explain how to derive the performance of slotted aloha, you should know what I am talking about, right. You just can't say what is slotted aloha at that point in time. Okay. So textbooks, there are primarily, this will be the Raj Jain's book, which is this one, Art of Computer Systems Performance Evaluation, right. This is a good book. It is easy to understand. There are still some errors. I hope all those errors have been fixed, because it is 20 years old now, and but that is the other problem. It is 20 years old. He has not really updated this book. Not that the techniques have changed or whatever is written has not really changed much, but we just like to see some more recent examples and so on. And for that there is this alternative text. You don't have to buy this other book. It is should be there in Tata Book House, but this is a 1982 edition. I don't have the latest edition. I am hoping to get that. This is a book by Kishore Trivedi, which is the second book on your list. It is also an equally good reference. Very similar kind of topics are covered, and what is not covered in Raj Jain I will cover with special notes or some. I will give you handouts for those. Petri nets and so on might come later on. We will look at that at that time. Okay. There are several reference books too, which I have listed most, just to let you know there are also other books that talk about the same topic, but very rarely will we have to go to those textbooks also. So the topics that we are going to cover, right, in rough order. First is the basics of what is performance evaluation, right, what are some of the important techniques for performance evaluation, and what are the things to be considered, right. There are two parts. One is how to do performance evaluation in the sense of what should be the end result, right, and the other thing is techniques, right, specific techniques like Markov chains and Markov modeling, probabilistic analysis. Those are the techniques part, but there is another solid part which most of us tend to forget. If you look at many of the BTech projects, MTech projects, right, you develop a system and then at the end of it you say I have implemented the system, done, right, and then is there any measurement done on it? If you do a measurement, then how did you measure, how did you compare? These things we will talk about in the rest of the class this week also, but that is the basics of what is performance evaluation, right, what are the expectations of a good performance evaluation. That is the first part. One that like couple of chapters in Raj Jain's book, easy reading, we can quickly go through those points in 2-3 lectures or so. And then we will start with a little bit of random variables. So the initial random variables, stochastic processes, a little bit of overview, and then we go into queuing theory, which is the actual derivations. And you might have seen 604, right, the results of queuing theory which we briefly applied, but now it is we'll start with the Markov chains and birth truth processes and so on, which are sort of generic techniques. You can use this in many cases, and we will see examples of how we can use that for in this context queuing theory, and as time permits we will see examples from networking also. Okay. So queuing theory, single server, network of servers, mean value analysis, all these are tied together, right. So that is the first major chunk of this course. That will be probably about your quiz one time. Then stochastic bit range is also another module, which is, so these are the main theoretical techniques that I have listed, and if I end up covering these two very fast, we will add more, right. There are lots of tools and techniques. Either we will do more techniques or look at more case studies of how these techniques are used in terms of analysis. Then we will move on to discrete event simulation. So there are three types of performance evaluation techniques. One is analytical modeling, mathematical modeling, which we will, again, this is only scratching the surface. Do not expect to know all the different tools in the world and as to how to do performance evaluation. It gives you an indication, some bare knowledge you can start with, so you can feel confident that later on some other technique comes up, you can still go and use those techniques. So simulation is the second part, which many of us do, and in networking particularly, a lot of you use NS2 or have used NS2 and so forth. So that will be the simulation part. Again, what is simulation, how do you do simulation, what are the basics of a DES system, and one should know some of the stopping criteria, all those things will come later on. Okay. Then once I have this basic techniques, two techniques covered, the third is experimentation, which I will not get into because there is right, you have to simply implement systems. Then we start in actual terms of, okay, what are the things to measure, how do you identify those things to measure, what is the meaning of a workload, right, how do you characterize workloads, and then a little bit on data presentation, how to compare two systems, right. All these are based on the confidence intervals and so on. So that is when we do the implementation or do the experimentation, implement the simulator, then we have results, and how do you process the results and how do you present it, right. And some of it is simply heuristic, but at least you should know what the meaning of, when I say the zero, what is a zero confidence interval, or sorry, if the confidence interval contains 0 or not, right. Those things we will talk about later on, and then finally case studies and applications, and most important. So then I was planning on 2 or 3 programming assignments. I just want to introduce discrete event simulation to you, and therefore we will implement some protocols or some mechanisms in that. Okay, so this course deals with the performance evaluation of systems in general and computer systems in particular, networks or architectural systems and so on. So why do you want to do performance evaluation? What are the goals of performance evaluation?
To compare, help you make something to compare, to
okay.
make a benchmark.
Okay, so one is to compare two systems, right? Okay. Right, 2 or more systems.
For example, a system works with 100 users, and in future the system expects some 1,000 users.
Okay.
Then that scalability should be possible. So we predict that scalability with performance.
Okay. So to I guess to plan for future expansion, right? To see if your system, right, will be able to okay. Yeah, so scalability is important, right, especially when we talk about systems today where we are 1,000 users was satisfactory, right. Searching in those days meant searching in a relatively small database. Now it is a global database for pretty much everything, right. Okay, so comparing systems, determining feasibility for future expansion. What else?
Solving problems like bottlenecks, especially in complex methods.
You read chapter 1? Okay. Yes. So the second is to identify performance bottlenecks, right, or third rather. So to identify right, so bottlenecks in any system, right, can come from different places. If you look at computer system, right, there are several subcomponents, several subsystems, right. You have memory subsystem is there. Within memory you have your cache management subsystem, then you have a hard disk system, right? There is a file subsystem also. So there are several subsystems, and then you find that as you add more users or the system or the CPU gets faster, you are still not able to get the performance improvement that you were expecting, right? So therefore you need to find out which of these subsystems is actually causing the problem, right? In a typical system, for example, we know by now that your IO system, right, is a major bottleneck. Your hard drive system, your hard disk system is also a bottleneck because your file system is not as fast as your main memory system, right, and so on. So there are these are, so despite having a faster CPU, you find that some of these other systems contribute to your system being slow. You need to find it out, right? So that's one of the is to find out where the bottlenecks in the system performance are. Then
to remove or fix existing bugs, it's a single system, so we might have some problems in that. So
the performance problems or functional problems? The functional problems, your performance evaluation will not necessarily tell you, right? Well, if you are doing scalability analysis, yes, you will do performance evaluation for a large system. You find that whatever work for 100 system, 100 users not working for a million users could be because your algorithm is running very slow, or could be because you have some hash define that says hash define max users 100 and then your system fails when you go to million users, right? But that is more of a functional issue than a performance issue, right? So that assume that your system is functionally tested and you know that it will work well for X number of users. As to how well it works is what we try to find out. Any other uses? You also would like to, for in any system, right, there are several parameters that you have to tune, right? Your system depends on many parameters that can be set. For example, in operating systems, right, page size. How do you know which is the best page size? Is it 4 kilobytes or 8 kilobytes? Should I have 32 megabytes for the page size? Some way we have to figure that out, right? You know that I can build a system for any page size, but for a system to operate correctly, optimally, right, you need to find out so called, this is what is called as, right, parameter or system tuning, or that does not look right. You will edit this, okay, right. So parameter tuning or so called system tuning. Right, you should find the right operational parameters for any system, and sometimes it is not possible to simply guess as to which is the right one. You have to try out several combinations of the system and then you say that okay, this is indeed, right, something that works. For in the case of OS you have cache, again you look at the hard drive also, right, what is the best block size, right? But block size is determined by the hard drive, but there is also something the OS can decide, right, what is the minimum number of bytes I will transfer to and from the file system, right, that also will determine your system performance. So there are several things to be tuned and set correctly. If you look at networks, again even if you are in TCP, right, in TCP there are also several parameters to be tuned. Can you think of some?
Window size.
Yeah, window size, right. So how did people decide that 16 bits is adequate for the window size, right? They thought okay, randomly 16 bits, therefore larger size is 64 kilobytes. You find that 64 KB is not enough, right? How do the receiver and the sender agree on some appropriate window size? That is one. And so like this you will find several system parameters that will have a serious impact on your system performance. If it is set, if you set the congestion window a very small value, then you will find that your performance is not satisfactory, right? You won't be able to get the maximum efficiency from your TCP or link level protocol that is operating. Okay, so these are, right, some of the reasons. Anything else that comes to mind as to why you should do performance evaluation? So fine, we will start this, we will leave this as a right adequate reason to look at performance evaluation more seriously. Okay. So then what needs to be done before I go to how, right? How is, okay, either I use Markov techniques or maybe theoretical models or mathematical models or just simulation or implementation and so on. There are a few set of steps, right, that one needs to do. So we will just go ahead and list those. So that is the why, then we will look at the what. So this book actually has 6 parts and each part roughly covers one of these 6 different things that has to be done. Okay, so we will kind of write that, and it is self-explanatory, so I do not need to. So first is to select the appropriate evaluation techniques. So assume that you have somehow built the system, let us say implementation has been done. So you need to define certain things. One is okay, what kind of experiments you are going to build, right, and then what are the performance metrics, as well as system workload, and so on, right. So one has to define what is it that I am trying to optimize. A system can be measured, the performance of a system can be measured with several metrics in several different ways. A simple example is if you look at a network, delay is one metric, right, response time is one metric, other is throughput, how many packets per second are being handled by a particular router and so on. So those you have to first of all quantify, which of these are important, that makes sense. You can also take delay and say is only main important or is variance also important, right, that is another extra, or even look at the third moment, fourth moment and so on and see are all these important or only some of these are going to be important. And the next is what kind of workload, right. If you look at our wireless systems today, right, our cellular systems, it was mostly voice data. So mostly people optimized on making sure that the voice calls went through, you had large number of voice calls accepted with good quality of service, so you don't hear all this noise and so on. Then slowly data started coming, people started using more of data calls, right. Then you have now your workload start changing now. So now I have 80% of the calls are voice calls, 20% is data, but over years that may change, where most people are simply using regular landlines. So cellular is mostly for wireless now, it is only the primarily internet access device. So it becomes 80% data, 20% voice, then your workload starts changing, right. So you have to sit down and think what are the possible ways in which your system workload can be characterized. And then it gets even worse when you say okay, people are using this for internet, for GPRS, 3G, whatever it is, and then there is a large bunch of people simply watching TV, right, on their mobiles. So now you have to look at it and say okay, 30% voice, 30% data simply downloading, another 40% is for video traffic which requires much higher fidelity, and people won't tolerate drop frames and things like that. So therefore your system workload characterization is also a very important step. That is the first part you would say. You have to work out several such scenarios, right, and then say okay, these are the possible scenarios. The problem is that this can be infinity, right, the number of scenarios can be infinitely large. So you have to use your judgment as a performance evaluator and say I know how the system should behave, these are typical scenarios, you will present those cases to your for evaluation, right. So that is your first step. So we will look at these a little bit later in terms of this workload characterization and so on, right. So once I define what experiments to conduct, right, so then I should do my performance measurements correctly. So now you run your experiments, right, collect the data, and this is more or less routine stuff that you would do, right. We have seen that in enough labs as to how to collect data from performance measurements and so on, right. Then once I get the metrics that I measure, right, then you need to do some sort of statistical analysis, right. So you simply can't say that system A is better than system B based on a few tests. So there has to be a little more rigor in the way that you will compare two systems, right. So that is where you will have your use of statistical techniques. To compare alternatives. Okay. So as an example, let's say you have your own fancy sorting algorithm. You know that there are so many existing sorting algorithms, right, or you would see them in ADSA and other courses anyway, right, and you have your own sorting algorithm, and then at the end of it you have designed it, implemented it, and then you want to see whether yours is better than the other systems, right. Then you should have conclusively, statistically you should be able to say that your system is definitely better than all the other existing systems, and then sometimes it will be possible, sometimes you will be not able to say that there is statistically different, this system is statistically much better than any other existing system. It will be good in some cases but bad in some other cases, right. So depending on how your algorithm is designed. So you need to have some proper techniques that really tell you that either it is definitely good, right? You can't say yeah it is more or less good. That is not really adequate. You have to have rigor when you say that I am comparing one system versus another system. Then the actually some of this is in little bit out of order, right? This design of experiments should have come before, but the book is kind of organized this way. So design right, simulation experiments or whatever it is, right, simulation, measurement, in such a way that you get maximum results with minimum effort. We will see what this means later on, right. For example, if you are trying to measure different metrics in the same simulation run, you should be able to get all the metrics at the same time, right, rather than have to have multiple runs of the same system, each for a different metric at different points in time and so on. So how do we identify the important factors that affect a system performance? I will define those later on, right. What are the factors that affect a system's performance, which of those factors do you vary, and then how do you get the resultant performance analysis, right. So this is another part that tries to tell you how to design, right, how to identify what are the factors and how to combine factors together and so on. Then we will come to 5 here, right. This is the second two parts are actually relating to the techniques themselves, right. So if you use discrete event simulation, you can use the simulation also, it is a tool, it should be used correctly, you can use it incorrectly also, and when we go later on we will see how people end up actually using this incorrectly. So how to design, right, design of so the classic question that people ask is, I have a simulator, I am running the simulator, right. Let us say you are processing some requests, the packets coming into a router, you have implemented a new scheduling algorithm for a router, and then you run the system for several packets coming in at different points in time, and then you are measuring the system itself. Then the question is, when should I stop the simulation, right? In the case of a mathematical model, you simply have to apply your formula, you run it, and then you will get a number. You say, okay, this is the mean delay, this is the mean throughput, you tell this is the value, you take that and go home. But in the case of simulation, you can run it for 1000 time units, 1,000,000 time units, 20 million time units, right. When do you know when to stop? How do you know that your simulation has reached some sort of steady state where there is no point in running the simulation any further, right. If you stop the simulation too soon, then you end up with mostly a transient behavior in the system. If you run it for very long, right, my students will tell you that each simulation will run for hours together, right, and then we vary several parameters, and then you have multiply that by the number of hours. So we can quickly run into a combinatorial explosion when I have several factors, each factor taking several possible values, right, and then it takes a very long time. You will never finish your BTech or MTech project, right, if you really let everything run for a million seconds and so on. Then how do you know that you actually achieved some sort of steady state? So these are things that one has to know so that you design your system efficiently. Otherwise you will simply run it for, okay, I am going to run it for 10,000 units, I hope my advisor won't see that, and therefore there are some results coming out which seem adequately. That is the 5th part of this book, and a little bit of course also we will talk about, right, what simulation is. So you understand when you run a simulator that there are some things to be dealt with in the simulation itself. Then the last part is actually the mathematical techniques. And there are several mathematical techniques. We will only focus on some that gives us an inkling of what is going to be there, right, what kind of systems are there. So this will be largely queuing systems, right, to a certain extent, and to understand queuing systems better we need to use some little bit of Markov chains and Markov processes, understanding that, and all the other things I mentioned before, mean value analysis and all those things will come in. Okay, so this is roughly, right, the 6 major components of this textbook, and roughly what also we will try to follow.
What is the difference between first one and fifth and
Okay, this is actually defining what you want to measure. Yeah, okay, that is whether you want to use simulation tools or mathematical tools or experimental tools, right, that is the first step that you will try to do. And then you decide what kind of the performance metrics that you want to measure.
What
Okay.
How do they decide? Considering I know which technique will give them best performance.
It's a matter of okay. It's usually what you do is you try to do all three. Okay. The classic thing is you never trust your simulation, right? We will see examples or see case as to what the particular characteristics are. Simulation will give you a good abstraction, but simulation the problem is resource constraint. It may take a very long time to get good results with simulation. Analytical techniques will be able to get quick results. You can put it in MATLAB and get a formula, even with iterative you can still get the results fairly quickly, but mathematical techniques will make a lot of assumptions. So you will abstract the system away so much that you miss out on the finer details. Your system will mostly black boxes put together. In simulation you can also get more detailed performance metrics in the case of a simulation. You can measure everything that you can in a simulation. In the analytical model you probably cannot do all the kind of metrics that you want to measure. Then third is about implementation, where there is depending on the system complexity you might implement, you might not implement, but ideally what you do is you start with mathematical modeling, right, which actually is supposed to be part 2 or next part of this lecture. You start with math modeling to get an asymptotic understanding of what the system behavior should be, and then you say okay, right, with for example queuing theory, alright, mean delay I can measure with my queuing model that it is 10, we saw that right with networks, it is 10 seconds per packet and so on, but you want to know more about how about the packets which have this particular packet length, right, you want to know for the different packet lengths what the corresponding delays are. You don't care about just the mean alone, you want to know more, then you have to go into simulation because your analytical model will not help to do that. Then you go into implementation, right, then you start suddenly seeing that your system, right, operating system or whatever it is will start imposing serious constraints on your own, on the performance itself, right. So then the implementation is the best, but before you go there, so usually what happens is you have say 15 possible techniques, right. Look at sorting as a classic example. There are several ways to sort. You first do your analysis, say time complex analysis, that says that okay, this insertion sort is probably not the best to do, or bubble sort is not the best to do because of its high complexity, therefore I should go to something which is closer to, right, your n log n complexity. That is where your theoretical model comes in. Then you implement that, then you find that in the implementation, right, 2 order n log n algorithms will be totally different, right, will have different behavior when it comes to actually running on various systems, right. So it is not that theoretical complexity reduces your search space from say 15 algorithms to 4 or 5 algorithms. Then there are empirical issues that come in, right, that we will understand with simulation. Then you really put it in a system and then say what happens in the system where there is a more realistic workload, where there are, like look at searching for example for queries, right, on the web, where you have your own searching algorithm. Then it's a totally different domain. Here is a very controlled domain when you put it in a simulation environment, right, whereas in a real system, because in a simulated environment you vary the set of parameters, the number of the size of your data set based on what you decide, but your real system might be on a totally different workload, right. So you want to see on a realistic system workload how it happens, so you keep reducing your search space. So when you go to implementation you will probably have only 2, you start with say 15, bring it to 5 in simulation, then you come down to okay, these 2 seem to be the most promising, therefore I will do it in that particular case, right. So that is the way that you will normally scope down to what you want to implement, and finally what you will implement you will turn out to be the most simple one, because the more complex the system is, the harder it is to actually implement it. So you find that many times simpler solutions work better than complex solutions, but that depends on the problem, sometimes complexity is needed and so on, right. So that is what this is, and then these are, right, how do I compare 2 systems? We will see this later on, we saw this in networks class also, right. Is waiting time the best thing, or is it the total time spent in the queue, right, which is the most important metric? You choose the wrong metric, you might say that one is better than the other, so therefore the choice of metric is also very important, and not just mean, right, I said mean, variance, and several other factors, right, resource utilization. From the system point of view, a link has to be utilized to the maximum possible extent. When a system utilization is very high, what happens to the user, we will see this later on, right, the user will see very high delays in the system. So if you want to add as many people's hostels are now fully loaded, right, because we want to keep the utilization very high, but then what happens, people are unhappy. So there is always this global utilization which the system wants to happen, wants to see, and you have the local utilization from the user perspective, you want only the whole floor to yourself, right. So there is no trouble whenever there is nobody around you, you have all the freedom of enjoying this nature. So you have always this classic tussle between those 2. So choice of performance metrics is what will make a big difference. And then workload again, right, so how you characterize that is really more of an art than anything else. You should know how the system is going to behave, and if you talk to some of the students in our labs, this workload characterization is so hard, right, we might come up with a set of scenarios, then usually we fall back on, so what do we do normally, we look at benchmarks, right. You say that okay, here is my spec-in benchmark, here is my whatever system, right, simply run on it, and submit the spec benchmarks or whatever it is and say that on this benchmark my system is beating all the other guys. That is what you will see typically in all the newspaper magazine ads, right. Why? Because it is a convenient cop out. Somebody has said this is a possible workload, run it on these systems, and then you show that this is my one number or whatever you compute, or maybe several numbers you show, and that is where workload characterization becomes a challenge. You simply depend on some system experts who know the system for 15 years or so, that will tell you, right, what to do. So that is where this workload part comes in.